Now we're going to talk about motion graphs. Motion graphs we like to use because they give you a lot more information than a motion diagram. Remember, we talked about motion diagram was just the dots, equally spaced, equal time intervals. A motion graph, you actually plot position versus time, and then velocity versus time, and acceleration versus time. And you plot them all over the top of each other because the time is the same for all of them. And we relate how the position changes versus the velocity versus the acceleration and how they're interrelated. Remember that velocity, we already talked about, is the change in position over change in time, if we're looking for instantaneous. And the acceleration is the change in velocity over change in time. Well, all that really means is that the slope of this graph is this graph, and vice versa. So when you're taking the derivative, this is a derivative, you're just taking the slope of the line. So the slope of the line of the function x versus t gives you the velocity. The slope of the velocity versus time gives you the acceleration. So for example, let's say I have a constant acceleration. Well, that means an object would go like this. So its motion is like this. What that means is it's going in a nice straight line. So for every time interval, it goes the same amount of distance. That's how we know it's constant velocity. And if you look, the slope of this is going up, so it's a positive slope, but it's not changing. So the velocity versus time graph would look like that. So the slope of this line is a positive number. Remember, these are 0 here. And so it's a positive number, but it's not changing. And then what about the acceleration? Well, the acceleration is the slope of the velocity graph. The slope of the horizontal line is just 0, and so the acceleration is 0. This would be the case when you have a constant velocity. What if you have something that is speeding up? So you got x, v, and a. This is x, velocity, acceleration. We want something to be speeding up at a constant acceleration rate. What that means is it starts with a velocity. In this case, I'm going to start with 0 velocity, and I'm just going to speed up with a positive velocity. Yeah? What's that mean about the acceleration? Well, the acceleration graph, remember, is the slope of this one. Well, this is now a positive slope, but it's not changing. So this would be a positive line above 0, but constant. But what about this one? This one's a little trickier because we have to think about it right now. Right at this point right here, it has 0. Right? Its velocity is 0. Okay, which means it has a slope of 0, so it's horizontal. But then over here, the slope is increasing, the slope is getting higher and higher. So it's got to be a higher and higher positive slope. So it goes from 0 horizontal to a higher and higher positive slope. So on this graph, right here, it would look like this. The position versus time graph, remember these are all time here, is actually a parabola. It's a positive slope, it's a positive parabola, meaning it's opening upward. And the slope of the line is 0, then the slope gets higher and higher and higher as we go in a positive direction. Hopefully this is making some sense. What if we have one? We want to do a slope versus, or our motion diagrams. Let's do it for our same one we did before, where we have a ball and we throw the ball in the air. And then it comes down, we catch it again. velocity, this is position. Okay? So we don't do ball because I have a marker in my hand. If I throw the marker up in the air, it comes down, I catch it. I want to do that on a motion graph. Okay, so the position it starts with is 0, but then it goes up to a certain point and it comes back down again. But when it starts, when it leaves my hand, I give it an initial positive velocity. Okay, so it has a high positive velocity, but what happens to that velocity as it goes up? That positive velocity gets slower and slower and slower, and at the top, the velocity actually goes to 0. And then when it comes back down, it has a negative velocity. So I'm going to do the velocity graph first. And what you see is it looks like this, where it starts with a high positive upward velocity. It goes to a point here where the velocity is 0, just for a brief moment. And then it goes down and the velocity becomes negative. Okay? So what that means is we start with a high negative slope here, right? Positive velocity. So we have a positive slope that goes to 0. So that means when it starts the position here, it has a high positive slope and it's going to go to 0. And notice that this time has to line up here at that point. That's where the velocity is 0. That's where it's at the top of the arc. And then at this point it starts to accelerate back down, comes down to here. Notice that the velocity here, you have a high positive slope, slope is 0, slope goes negative, and it keeps increasing more negative the further you go. All right, what about the acceleration? Well, the acceleration here, you have a negative slope, but it's a constant negative slope. So when you have a constant negative slope, you're going to get a line down here. In fact, we know what this value is. This value is g, which is 9.8 meters per second squared. Little g is just the acceleration of gravity on the Earth. And it's negative because it's pointing down. All right? So our standard convention is to make positive up, negative down. Physics work fine if you flip it all right. You just have to be consistent when you do it. So this is what it would look like in a motion graph for throwing an object in the air and then catching it when it comes back down. That's how you do motion diagrams. And these become way more complicated the more things you have happen, the more things accelerate, decelerate.